And today I'm going to mainly speak about Laplace integrals. There are other topics very interesting, but we're not going to have time to do that, so I will just point it out for you, for those who are interested in the topic. But essentially today we are speaking about Laplace integrals. And to begin with, let's speak about a very simple example. Do you know what is an integral from minus infinity to infinity of e to the minus alpha t squared dt? Or let's write it as x t squared dt. What's the answer?
Square root of pi over x.
Thank you very much. Square root of pi over x. How do I do that?
You can go to polar coordinate.
Well, I mean completing the square, right?
Yeah.
Writing it as the integral of e to the minus x t squared plus q squared. I don't know. So this is, if this is I, then I squared is the integral from minus infinity to infinity double integral. T squared dt dq, right? This is I squared, and now I can go to, I can write it as 2 pi. I mean, this is the integral from 0 to infinity of r e to the minus x r squared r dr, and this is, and now I can change variables. So if s is if s is r squared, say, then ds is r dr. So this is 2 pi integral from 0 to infinity of e to the minus x s ds, which is 2 pi over x, right?
It's ds over 2, right?
ds over 2, of course. So ds is 2r dr, so this is ds over 2. So the 2 cancels out, so this is I squared, and I is the square root of that. Okay. Now, suppose I would like to know what is the asymptotic behavior of this integral as x goes to infinity. So the way I will, so and okay, to be for the sake of simplicity, let's take the integral from 0 to infinity dt e to the minus xt squared, and I want to analyze the asymptotic behavior of this integral as x goes to infinity. Of course, it should be a very small number, because if x goes to infinity, it falls very fast with t. So I will get contributions. Okay, now I took it from 0 to infinity because you see this is from minus infinity to infinity. It is going to be 1/2 of that. Okay, so we know the answer, right? The answer for this integral is 1/2 square root of pi over x. And now suppose I would like to analyze it using integration by parts, the way we did it last week. So I will write it as the integral from 0 to infinity minus d dt of e to the minus xt squared dt, right? And here I have 1 over 2xt. Right? This is just an algebraic manipulation. So this will be equal to minus integral for the limits will be 0 infinity, and here I have e to the minus xt squared over 2xt plus the integral of the, of VDU or whatever it is, right? But the point is, first of all, that this diverges because of the lower bound, and not only that this diverges, it is going like 1 over x. So even if I find a way to somehow to somehow overtake this divergence, the divergence that is coming from the t equals 0, because I will move it to some finite epsilon value, I still have something that is going like 1 over x, not like 1 over square root of x. Okay? And so all in practically, I mean, it depends on the answer, right? But when the answer is not integer power of x, the integration by parts is not working. So we have to figure out a different trick. Okay. So the way this trick goes on is very interesting, because we are going to work in two steps that are that appears to be to contradict each other, but still we are going to do that, right? So what is a general behavior of the general statement of Laplace integral? Let us assume that we want to calculate the following integral. I have an integral from a to b, some limits, of some function of t, e to the minus x times another function of t dt. Okay? Now I want to, this is hopeless integral in general, because phi and f were not defined. Okay? However, I'm going to ask not only not what is the answer, what is the solution for this integral, but what is the asymptotic behavior of this solution as x goes to infinity. Right? That's the important point. Now, let us assume to begin with that this is A, this is B, okay? And this is phi of t, between A and B. What we can say about the contribution to this integral?
It would be from the bounds.
Sorry?
It would be bigger from the bounds, right?
Sorry.
From the maximum.
Okay? You see?
Now it blows up
Blows up
as x goes
if
to
x
infinity.
is infinite,
Yeah.
right?
Yeah.
But we can say we now want x to be larger than any other important parameter in the problem. So clearly the main contribution to the integral here, this is the crux of the story. If you don't understand that, you will get lost. So please, if you have any question, let me know. The main contribution to the integral will come from this point where phi has a maximum. You see why is that? Okay? So if x is small, then maybe this f of t will have a peak here and will dominate it. But if we keep f of t fixed and phi of t fixed, and we are increasing x, at some point the dominant contribution will come from this region, from the region where phi has a maximum. Okay, I assume that it has one maximum. If it has two maxima, it will come from the highest maximum. The dominant term will come from the highest maximum. If it has two equal maxima, it will come from both. But, okay, you understand what I'm saying? Are you okay? Good. So, what we are going to do is to say that as x goes to infinity, what I'm interested in is the behavior is a contribution that is coming only from the vicinity of the maximum. Okay? So, I would say, okay, this is now asymptotic to, right? Asymptotic to, at the limit, in the sense of asymptotic that we worked with all this semester. to the integral from c minus epsilon to c plus epsilon of f of t e to the x phi of t dt. So I took the integral and I limit the integration. Instead of doing the integration from here to here, I am saying I can do the integration only from c minus epsilon to c plus epsilon, right? This is c plus epsilon. This is c minus epsilon. All the rest of the integral is subdominant as x goes to infinity with respect to the green region. Okay? Good. And no matter, I mean, of course, then for every epsilon there will be x that is big enough such that the green region will be the dominant and all the rest will be subdominant. Therefore, I can write now that this is equal to f of c, okay, times, and now I will say that phi in this green region, the green phi, the green phi is phi of c minus 1/2 minus or plus, I have to think about it, phi double prime at c times t minus c squared. It's a plus because the second derivative turned out to be negative. Right? Okay, let's write it here. Just to make it explicit that it goes down both sides of the mass. Okay? So I wrote f of c times e to the x phi of c, okay, times the integral from c minus epsilon to c plus epsilon on e to the minus 1/2 phi double prime of c t minus c squared dt. Okay? Do you understand? Please stop and ask questions if you get lost, because that's the main story. Everything will be yet another implementation of the same thing. Good. Now, how we are going to solve this integral?
Gaussian.
Okay, this is a Gaussian integral. Of course, I can now change variables. Instead of t minus c, I can call it, I can change variables. This is completely technical. So let's define s as t minus c, and we are going to integrate from minus epsilon to epsilon over ds e to the minus 1/2 phi double prime of c times s squared. Okay? Times x, of course. Okay? However, okay, now here I'm going to do something that looks contradictory to what I did until now. Now I would like to say that this is asymptotic to the integral from minus infinity to infinity of ds e to the minus 1/2 x phi double prime of c times s squared. So I started by saying I don't care about what happened between A and B. The only important contribution will come from the green region. Now, after approximating everything in the green region, I'm taking the limits of integrations back to plus minus infinity, because again, everything outside is subdominant. So who cares? Okay, that's this is I mean, first I'm saying, who cares about what's happened outside? So I will focus on the green region. And now I'm saying, since everything that happens outside is subdominant, then I can extend the green region to infinity. Okay? And now I know what the answer, because the answer for that is, this is just this, right? I didn't copy so I have, okay, this is just this. So, and the answer for that is what? Is
the square
root of
Phi
2 pi
over
time over x times phi double prime of c.
What if you're on a solid point? What if we are on a point that the second derivative also vanishes?
Thank you very much for the question. I will address it in 10 minutes. Okay? So all in all, we say that the asymptotic behavior right? The asymptotic behavior of I as x goes to infinity, the asymptotic behavior of I is what? Is f of c e to the x phi of c square root of 2 pi over x phi double prime of c, absolute value. Okay? If. What are the conditions?
The second derivative is that.
The second derivative, we want a maximum where the second derivative is not 0, right? And there is a maximum c between a and b, right?
There's only one, right?
So we ask c to be between a and b. This is one. C is a maximum point.
If we would have two degenerate maximums, it would be 2 times.
Yes. And phi double prime, not 2 times, because it will be phi of one and phi of the second one. Right? And also z. And we want phi double prime to be non-zero. These are the two conditions. Actually, there is a third condition that I am hiding for the moment under the carpet, but it will appear. I mean, later we will discuss it. Okay? Good. Now, what happens when these conditions are not fulfilled? Okay? So, one possible case maybe I have to allocate more room for the. Okay, let's go with that. This is first possibility, right? Now let's discuss another case. The case where if this is A and this is B, okay, phi of t looks like that. So there is the maximum point is the left boundary. Okay? Now, because the maximum point is the left boundary, we know that phi is now, first of all, again, we would like to look only at the behavior of the integrand here, right? Between a and a plus epsilon. So we are going to write this. This is asymptotic too. integral from a to a plus epsilon, okay, over f of t e to the x, and now I can write, I will do two steps at once, right? Now I'm writing x times phi of a minus phi prime of a times t minus a dt. You see, unlike when the peak was in the middle, it was a maximum, and the first derivative was 0. So the first contribution to the Taylor expansion around the maximum was the second derivative. If the peak, if the maximal point is at a, there is absolutely no reason. It may happen that it's also a maximum point, but in general, generically, it will not be a maximum. So I will get this, and therefore I will approximate that by f of a e to the x phi of a integral from a to a plus epsilon over e to the minus x phi prime of a absolute value s ds, where s again is t minus a. Okay, and now all I have to do is so this is from 0 to epsilon. From 0 to epsilon if I change variables to s. Okay, and now I can extend it back to infinity, and what I'm going to get is f of a e to the x phi of a times divided by x phi prime of a absolute prime. You see? So this is, so if C is A, maybe I will write everything each. So if C is A, okay, generically the solution, the asymptotic will be I is equal to f of A e to the x phi of A divided by x absolute value of phi prime at A. Okay, now I will let you prove to yourself, of course, that if C is B, then I will be f of B e to the x phi of B divided by x phi prime of B absolute value by the same token. Good. So now the other possibility that we have to take into account is the possibility that we are, again, this is A and this is B. The maximum point is between A and B, but this maximum is not quadratic. So the first, we are going to, we can write phi around this point in the green region. In the green region, we can write that phi of t is equal to phi at C minus phi p at C. That's a piece derivative of phi. If p is 2, we should get the same answer as we got here, right? But now let's say p is 4, right? That is fourth derivative, and we have 1 over p factorial. That's and now I have x here, of course, and phi, and sorry, and t minus c to the power of p. Right, the first non-vanishing term in this expansion. Okay, so we are going to plug it here, blah blah blah. I mean, we are going to define the integral here, and then we are going to expand it, and s is of course t minus c, right? So clearly what we are going to get is f of c times e to the x phi of c, but now we have the integral from minus infinity to infinity after shrinking it and extending it and blah blah blah, to over e to the minus x phi, the pth derivative of phi at c divided by p factorial, times s to the power of p ds. Okay? So we have to solve this integral. What this integral is going to give us, by the way, p must be even, I think. Right? Because if it's odd, it's not a maximum. Right? P must be even. If for C to be a maximum, P it must be even. Okay, so what are we going to do? First of all, let's call all this, so we have f of c times e to the x phi of c, integral from minus infinity to infinity over e to the minus, let's call it alpha s to the p ds, where alpha is x, the pth derivative of phi at c divided by p factorial. No, I want to write it as alpha s to the power of p, and alpha is this to the power 1 over p. Just the definition. Okay? So now I like to define Q as alpha s. So if Q is alpha s, then ds is dq over alpha. Have I missed something? I think not. It's your job to figure out. Okay, so I have f of c times e to the x phi of c times the integral from minus infinity to infinity of dq over alpha times e to the minus q to the power of p. So I have 1 over alpha here. Right? Now, okay, because p is even, okay, I can write this as 2 times the integral from 0 to infinity. Okay, and now I have, okay, yet another change of variable. So what you suggest? I used S, I used Q.
No,
T, I used T also. Theta.
W.
W. Okay. So W will be Q to the power of P. So I have 2 f of c e to the x phi of c divided by alpha, and now I have an integral from 0 to infinity over, so q is w to the power of 1 over p, so dq is 1 over p w of 1 over p minus 1 times e to the minus w dw. Now the 1 over p goes out, and what remains is a gamma function of 1 over p. Okay? So, all in all, what we have, after all this hard work, what we have is a general function which actually included this, but it's better to write it separately, which is that I is asymptotic to what? I have 2 f of c e to the x phi of c divided by alpha. Now alpha is x to the power of 1 over p times the p's derivative of phi at c, again to the power of 1 over p, right? And now we have p factorial to the power of 1 over p, go upstairs, right? And now we have 1 over p times, this is gamma of 1 over p, and 1 over p times gamma of 1 over p is gamma of 1 over p plus 1. So we have here gamma of 1 over p plus 1. This is a general case where the first derivative that do not vanish is a piece derivative, which, as I said, is even. Okay, so just the sanity check. What's happened if we plug here p equals 2?
You should get
I hope to get the same behavior. So the f of c is f of c, the e to the x is e to the x. So I have 2 divided by square root of x, which is x over 1 over p, times phi double prime of c, again in the square root. This is that. And now I have p factorial 2 is 2 to the power of 1 over t is what?
square root.
Is square root of 2. And I have gamma of,
3 over.
okay, let's write it as 1 over p gamma of 1/2, right? And this cancels that,
Square root.
and gamma of 1/2 is square root of pi, so I got the same answer. Okay. What's important here is to note that you see that as x is going to infinity, this term is going like 1 over square root of x. Of course, we have this that goes to infinity, but this part is going like 1 over square root of x. This one is going like x to the power of 1 over p, so the dependency is much weaker when p is 4 or 8. Okay? Good. So these are the main cases of a Laplace integral. Now that we are familiar with that, let's try to do a few examples. Okay? Again, we always ask the same question. I'm going to show you an integral, and we have to decide what the asymptotic behavior of that integral as x goes to infinity. Right? Okay. let's start making examples. I'm taking them from chapter 6 of the Holy Book. Right. So first of all, let's ask what is the integral from 0 to pi over 2 of e to the minus x tangents t dt. Right? This is I. And the question is, what it is asymptotic to as the x goes to infinity? So, what is phi? No, minus. Right? So phi is minus tangents t. What happened with phi between 0 and pi over 2? Where is the maximum?
מה זה target t? What is target t?
Tangent.
Oh, tangent.
Should I write it different way?
לא. חשבתי את זה משהו אחר.
Okay. Yes, that's tangent. So where is the maximum? Why 0?
Because
It's minus. If it was tangent, yes, then it diverges it. But now, because it's minus, we want it to be as small as possible, right? So clearly we have phi. So which case is that? Which case is that? Say equals say, right? So we can plug things in. What is f? F is 1. Phi is tangent t and f is 1. So what we have here is f of a is 1. We have e to the x times the value of phi at 0. What is the value of phi at 0?
0.
0. Okay? So no exponent. F is 1. E to the x phi of a is 1. So we have 1 over, and now we write x. And the next term is phi prime of a. So what is phi prime? What is the derivative of a tangent?
1 over cosine square. But the second.
This is minus sine over cos.
Right.
So this, so we have minus 1. Minus 1, I mean sine over cos. I mean, okay, we know that the tangent is going like t for small t, right? So this will be minus 1. Right? So the absolute value is 1. So we ended up with 1 over x. Thank you very much. Okay? That's asymptotic. Okay? Good. Another example. Integral from 0 to infinity of e to the minus x times sinh t squared dt. Okay, this is I. What is phi?
Minus inch square.
So phi is minus sinh squared of t. Okay? And what is phi prime?
Minus 2 inch.
Okay? Where this is maximum? The minus inch squared?
0.
At 0. At 0. You see? So apparently, in which case we are? The third one. This one. Again. However, there is a trick, as you will see immediately. So we know that this is going like close to 0. This is going like minus t squared. Okay? So we can say that this is going like integral from 0 to infinity of e to the minus xt squared dt. Right? And what is the answer? The answer, of course, is 1/2 square root of pi over x. Okay? Which is not 1 over x. Despite the fact that we have the maximum at the left bound, at the left,
The first derivative is 0.
because, again, yes, because the first derivative is 0. Right? So this is true only if phi prime of A is not 0. And if not, we have to do that.
It's like taking the second order on the Taylor.
Yes. Good. Okay. Now, next one, the integral from -1 to 1 of over e to the minus x times. Yes. Right. What is that? Again, this is the power of 4, and this is sin, sinusoidal function.
So the minimum is between, like the minimum.
Okay, phi is minus sine to the 4 of t. But note that it is between -1 and 1. Where is the maximum of phi?
0.
0. All of you see that the maximum is a 0? Okay? So the maximum is at 0. Now, how phi behaves close to 0?
Like this, that's like 4.
Right? So
Minus t to the-
phi behaves like minus t to the 4.
So the first, we need to take.
So the second derivative, we immediately know, will be 0. Only the first derivative will give us what?
Something finite, which is 4 factorial.
4 factorial, 24. Right? Of course, we can take the derivatives on the sign, but this will be hard work. Right? So we know that the maximum is at 0, and that we have the first derivative is the leading derivative, so this corresponds to the case p equals 4 in the horrible thing there. Okay? So let's start plugging things here. We have a 2. We have f of c, but f is of course 1. F is 1. We have e to the x phi of c, but it's again 1, because phi of 0 is 0. Phi of 0 is 0, which is this phi of c. Okay? So we have 2. F is 1, e to the x phi is 1. Here we have x to the power of 1/4 times the fourth derivative, which is, we say, the 24, right? So we have 24 to the power of 1/4. Now 24 to the power of 1/4 is, that's it. Now we have a p factorial, that's again 24, right? So we have 24 to the power of 1/4 here, above, and they cancel each other. And we have 1/4 gamma of 1/4, which is gamma of 1/4 plus 1. So this cancels that, and we end up with 2 over 4x to the 1/4 times gamma of 1/4. Is that true? Yes. Yeah. 2/4 is 1/2. Once upon a time, I was checking exams in waves, I guess, and there was a student that dragged along like 4 pages of the exam sheet the quantity square root of 4, and didn't manage to replace it by a better, by a simpler expression. Okay. Good. Now let's do something tricky. I want to approximate the integral from 0 to 1 of sine t e to the minus x times sinh squared of t dt. Let me just make sure that I know what I'm speaking about. Yes. In the book it's sinh. I don't. Okay, fine. I don't think it's valid, but okay. So let's see. What is phi?
Minus sinh.
Minus sinh squared of t. What is f? You see, we have an f. The f is sine t. Okay? Where is the maximum of phi? It's 0. Okay? So c is t equals 0. C is 0. However, Houston, we have a problem. What is the problem?
That sinh t is 0.
That f of c is 0. So if we want to plug it in this formula, we are going to have a problem because f of c is 0. Okay? Is that a failure of the Laplace method? The answer is no. Why? Because let's stick to the procedure saying that we first limit the integration to, right? If this is a and b, now it's 0 and 1, right? We first limit the integration to a very small region here, approximate everything for small t, and then extend it to infinity. Okay? So what we are going to get is an integral from 0 to infinity of t e to the minus xt squared dt. You see? So right, this is going to 0. Yes, the main contribution to the integral will come from here. Now, although we have something that goes to 0, right? But still it's the main contribution. Now this is solvable integral. Why? Because we can define now s as xt squared. And so t is s over x to the power of 1/2. And therefore dt is s is over square root of x, and now I have 1/2 s to the 1/2 minus 1. I don't want to write s to the minus 1/2, right? Which implies that what I obtained is the integral from 0 to infinity of 1/2, 1 over 2 square root of x, you see? And now I have s to the 1/2 minus 1 e to the minus s ds. Now what is that?
Gamma function.
This is a gamma function of 1/2. So what we got is gamma of 1/2 divided by 2 square root of x, y, I think that this is the wrong answer. Let me. Oh, okay. Because this is not the question that they asked. They want it with the fourth power. But anyhow, okay, that's a trick. You see? So essentially, the fact that f is going to 0 at the location of the minimum, of the maximum, is not a problem because I can still use this method. And clearly you understand that even if I have here sine t to the power of 6, say, then I will put here t to the 6 and it will still work with a different gamma function. Okay? As long as f is f have a power Taylor expansion around 0, I can use that. Even if f is formally 0 at the point of maximum. Okay. Well, this takes us to a more interesting question. Which is that I would like to estimate the integral from 0 to infinity, say, or to 1, or who cares now, of e to the minus xt minus 1 over t dt. Okay? Formally speaking, phi is what? What is phi?
It's minus t.
Minus t, thank you very much. And what is f?
E to the minus t.
E to the minus 1 over t. Now you see the problem. What is the maximum of phi?
0.
It's 0. But now f is 0. Not only that f is 0, it has no power expansion. So I can say, okay, at small t, it's t to the 7, and I will use some sort of a gamma function, because this is going to 0, f has an essential singularity at 0. What should I do?
What we did in the asymptotic integrals.
So, okay. Essentially, there is no way to implement the Laplace equation, the Laplace scheme for this story. However, there is a trick that allows us to overcome. Yes.
If t goes to infinity, can we just set it to 0?
If
t is large, can't we set it to 0?
But I don't think, I mean, the fact that x is large implies that the only interesting part of this integral is very close to 0. But I'm not allowed to go extremely close to 0, because then this will kill me. And there is no way to, yes.
We can expand the f in Taylor expansion and
No, there is no Taylor expansion for f around 0. That's the point. The problem is that f has an essential singularity. Again?
Some sort of boundary layers when we can.
I mean, okay, actually this is what we have solved with boundary layers, but this was when x was going to 0. Now we are speaking about x going to infinity, yes.
Can we try saddle point?
Thank you very much. Okay, we have to do the following. Okay, I will explain you what to do. So what we are going to do is, let's define, we have the right to change variables. No, I'm changing variables. So what I'm going to do is I will define S as t divided by x to the alpha not specified yet. I didn't specify it. Okay? So, and then I will get the integral from 0 to infinity of, so t is, sorry, maybe I want to do it, I mean, who cares? Okay. So t is sx to the alpha, right? I did a mistake, I should, but who cares? So I get x to the alpha here, and here I have the s. And now I have e to the minus x times x to the alpha times s minus 1 over s x to the alpha. That's the integral. Okay? And now, here is the trick. I will choose alpha to be minus 1/2. Why this is good? Because this implies that what I have is 1 over square root of x. This is that. Okay? The integral from 0 to infinity ds e to the minus square root of x. You see? The square root of x is in front of both things. Times s plus 1 over s. Great. Great. So now I have the large parameter is not x, it's square root of x. But otherwise, I can use everything in Laplace integration. So now, what if f is now 1, right? Because both of them are multiplied by x. And what is phi?
It's s plus
Phi
minus s plus
is minus s plus 1 over s. Where is the maximum? So phi prime is minus 1 plus 1 over s squared. You see? And what is phi double prime? Minus 2 over s cubed. Good. Where is the maximum of phi?
Plus minus 1.
No, but minus 1 is out of the integration
So 1.
regime. So this one implies that c is 1. C is 1. And if c is 1, then phi double prime of c absolute value is what? Is 2. No, absolute value. The absolute value kills the minus. Right? So this is 2. Okay? And which formula I have to implement?
the one that has non-vanishing derivative.
Wait, which one?
The second.
This one.
Yes.
Yeah.
This one. Good. So what I obtain is 1 over square root of x that I have from here, right? F of c is just 1, and now I have e to the note square root of x, very important because my large parameter is square root of x, it's not x, right? Times phi of c. What is phi of c? Yes. What is phi of c? What? Phi of c is minus 2. So I have here e to the minus 2 square root of x. Okay? What else? And now I have square root of 2 pi divided by square root of x divided by square root of x times 2. So the 2 cancels out, and what I have is 1 over x to the power of 3/4. You see, this one and that one, times square root of pi, e to the minus 2 square root of x. Did I omitted something? Let me just make sure that this is the right answer or not. Very good. Okay, so now that we have this technique, so this is the saddle point, as you say. I mean, all the Laplace integral is the saddle point. Let's make another example, which is even very useful. What is that?
Gamma.
It's a gamma function of x, by definition. Okay? So the question is, what is the asymptotic behavior of the gamma function of x when x is large? X goes to infinity. So first of all, let's write this as the integral from 0 to infinity of 1 over t e to the minus t minus x ln t dt.
So the idea is to do Stirling's approximation.
Yes, this should give us Stirling's approximation. Thank you very much. Okay? So, do you understand what I did here? This is just, there is no approximation here. Okay? Now, I want to use Laplace integration, right? Naively, if I would like to use Laplace integration, I will define phi as ln t, minus ln t, right? I will define phi as minus ln t, and then I will have a problem because the ln t, what can I say? Ln t, I should go to 0 in any case, because then ln t is minus infinity, so this is one problem. And the other problem is that the e to the minus t will give me again, no, what do I want to say? No, I want to take ln t to its maximum value, to infinity, right? So c will be infinite, but then the e to the minus t is have an essential singularity at infinity. That's my problem.
It should be plus x.
So it's the same problem as before, right? We cannot implement the Laplace integration, the naive schemes of the Laplace integration, because we have an essential singularity of the f. The f, right? The f of t is e to the minus t. What do I want to say? And this is 0 when t goes to infinity, and it has no power series expansion around t goes to infinity.
It should be plus x.
Plus. E to the plus, yes. So yes, and therefore ln t goes to infinity is a c. Okay. So again, I'm going to. So this cannot be implemented the way it is written here, and I would like to define s as t times x. What I did there. Okay, I will stick to that, although it's not good. So t divided by x to the alpha, just because I did it before. I don't like it. So what I will have an integral from 0 to infinity. First of all, I have x to the alpha outside. So t is x to the alpha s, and dt is x to the alpha ds. So I have x to the alpha d, and here I have No, I don't have x to the alpha because here I have the s over s. The 1 over t will cancel the x to the alpha. Okay? And now we have e to the minus x to the alpha s plus x ln of x to the alpha s. So I write it as ln x to the alpha plus x ln s. Yes. Okay? So, first of all, the e to the x ln x to the alpha goes out of the integration. Right? It has no s inside. And what remains is integral from 0 to infinity of the s over s e to the x to the s, to the alpha, sorry. S with a minus sign plus x ln s. Now I want both things in the exponent to have the same coefficient, which implies that what I am choosing for alpha? 1. So therefore I choose alpha equals 1 and I have e to the x ln x, which is good because you already remember it from the beloved Stirling formula, times the integral ds over s from 0 to infinity over e to the minus x times, or e to the plus x times ln s minus s. Good. So now we have a different set of Laplace definitions. What will be phi? Ln s minus s. What will be f? 1 over s. What is phi prime?
It's 1 over s minus
1 over s minus 1. And what is phi double prime?
minus 1 over s squared.
Minus 1 over s squared. Now where is the maximum?
At 1.
Is the maximum inside the integration? Yes. So which formula we are going to use? What? This one, again. The purple one. Okay? So we have the e to the x ln x here. And now we have to plug f of c. C is 1. So what is f of c?
1.
1. Next, we have e to the x times phi of c. What is phi of c?
Minus 1.
Minus 1. You see, because ln 1 is 0, and I have minus 1. So e to the minus x. And now I have to multiply it by the square root of 2 pi divided by x times phi double prime of c, but phi double prime of c is minus 1, absolute value is 1. So all in all, what we obtain is square root of 2 pi over x e to the x ln x minus x, which is Stirling formula. Right, so this is a Stirling formula as an asymptotics of the gamma function. Good. Which is, you know, I wanted to say that it behaves like n factorial, but x factorial, but yes. Good. Okay, and the last point I would like to emphasize here. So again, we have these formulas. They, at least in their spirit, they do work even when f vanishes at c, because we can just follow the spirit of Laplace analysis, focus on the region that is a dominant region, expand everything in this dominant region, and then expand the integration range. This is completely good. If f of c is not only 0, but if f has it doesn't have any expansion around 0, then we have to do this kind of change of variables, because if x is large, then also square root of x is large, and so on and so forth. Of course, it implies that we have to go to much, so for example, if we have square root of x, we have to go to much larger values of x in order for the asymptotics to work, but at least we have. Okay, so the last point I would like to emphasize is that suppose that we are speaking about right, this thing. Okay, so not only this thing. Let's assume that we have an integral from 0 to, who knows, b of some f of t e to the minus xt dt. Again, this is the integral, and this is, we want to take x to infinity. So all the contribution will come from where? From the immediate vicinity of 0, right? So phi, formally speaking, phi is minus t, and the maximum is at 0. Okay? So we can, and now let's assume that f of t in general have a power series, but not necessarily power series, Taylor series, but generic power series. So I can write f of t as sum from n equals 0 to infinity of an times t to the alpha plus beta n. Taylor series will be alpha equals 0, beta equals 1. But
can we do something similar in complex variable, like using Laurent series?
no, you don't have, you have this such an expansion. I mean, this is like whatchamacallit, when you have Frobenius.
Yeah, no, I know. This is for the
Frobenius type of
non-essential
problems.
singularity.
You have such an expansion, right? It's not Taylor, but of course, from the point of view of complex analysis, once you have here alpha, let's say, which is not an integer, then you have this tail, branch count. Then you have a branch count, and all kind of Riemann sheets that you can jump from one to the other, and so on and so forth. But okay, so so I can write it actually. First of all, I can expand the integration to infinity, because again, the green region is around 0, and I don't care. Everything outside is subdominant. And now I can write it as a sum from n equals 0 to infinity of an integral from 0 to infinity of t to the alpha plus beta n minus 1 plus 1, plus 1 minus 1. This, of course, is exactly that, right? E to the minus xt. Okay? Now I would like to make change of variables. I will define s as xt, and therefore this will be the sum from n equals 0 to infinity of an. Now, what do I have? Integral from 0 to infinity. First of all, e to the minus s. Now, the dt is what? Is ds over x. ds over x, okay? And now we have s to the power of alpha plus beta n minus 1, sorry, plus 1 minus 1 divided by x to the power of alpha plus beta n plus 1 minus 1, the same thing. Okay, now, what this will give me? So I have sum from n equals 0 to infinity, an divided by x, all these x's are going outside, and this x cancels the minus 1 here. So here I have alpha plus beta n plus 1, and what remains is a gamma function. And the gamma function of the same number, alpha plus beta n plus 1. You see? Now, this is all the terms in the series, right? It's not only the leading order as x goes to infinity. This is a complete asymptotic series, right? Where we use the idea that x goes to infinity.
Integration.
All the manipulations are completely kosher manipulations, no matter, right? So where the idea that x goes to infinity makes any difference here?
What is the substitution?
I did the substitution. That's it. So where I used the fact that x is large.
Replace the sum and the integral.
No, that's legal.
When you took b to infinity,
Thank you very much. Yes. This is where I assume that x is large. So all the other terms that are, I mean, because the result must depend on b, and it's independent. And the reason is because all the interesting activity should happen in the, so all the other terms that has to do with what happen above b are subdominant as x goes to infinity. So as x goes to infinity, I have this result, and it has a name, it's a very important result. This is called Watson's lemma. Who was Watson? I have no idea. It's not the advisor of Sherlock Holmes. Somebody else. Now, okay, and so this, I mean, it's an important thing because it shows you that not only you can get the first order. By the way, there are ways to extend the. You can, in this case, you can get the whole thing. By the way, before when we discussed things like the integral of f of t, right, e to the minus or e to the x times phi of t dt, right? We can suppose phi of t have it's right. Suppose the maximum is around here, right? We can make the substitution q is phi of t and end up in an integral like that. And if the peak is in the middle, we can divide the integral into two parts, right? So this substitution, with this substitution, we can use Watson's lemma to all the Laplace integral and get all the, but it so happens that in many cases this substitution is very complicated, right? But in principle, we can use this substitution and get immediately, with a simple formula, not only the first correction, but all the power series. Okay, this is the part. These are the parts of the book that I will have. I had the chance to cover during this semester. I just want to give you a few little comments that have to do with the other parts of chapter 6 that are very important, and I should decide what to take and what not to take, and this was my decision. So just to let you know in case you will need it, right? One thing is as I said, this is the full asymptotic expansion, order by order in inverse power of x. This is only the leading order, right? If you want the next order here, right? If you want to calculate, okay, you have 1 over square root of x, but what will be the next order? This is explained in chapter 6. It's not an easy task. You have to be careful, but you can do that, right? Another extremely important. Maybe I have to take out one lecture, and so one extremely important thing that I didn't cover is a case where you have an integral from A to B, say, of f of t e to the I x phi of t dt, right? And you are interested in the case where x goes to infinity. This is called not a Laplace integral, but Fourier integral. Fourier integral. Now, and why it is so important? Because it appears everywhere. Because in quantum mechanics and things, this is the integral that always appears. Okay? And what's going on when x goes to infinity? X is 1 over h bar in most cases. So, first of all, there is think about this as the only difference is the I. Now you can think about it as the cosine and sine of x phi. Okay? And if you think about it as a cosine or sine, doesn't matter, you understand something. You have an integral from A to B of f of t times, say, cosine of x t, say, or x, any function of t, dt. Now x goes to infinity. What will be the answer? Just qualitatively.
There would be some like very fast oscillation.
Yes, x going to infinity. So we have extremely fast oscillations. So it means that no matter what f is, if f is something like that, right? Suppose this is f,
We need to
right?
have some sort of gradient
But
descent.
it is superimposed on
Plus minus one.
these oscillations that will take half of it to be minus and half of it to be plus, and the answer will be 0. So there is a statement called the Riemann-Lebesgue something theorem formula, saying that when as x goes to infinity, this is going to 0. Right? If you take x big enough, it will go to 0. Now, okay, but x is large. From what will give us, so where we are going to get the main contribution here?
From t0.
No, it's A, B. 0 is not, okay? This is a Riemann-Lebesgue something. Riemann-Lebesgue what? I forgot the weird. See, should be written here. Lemma. Riemann Lebesgue lemma is saying that this must go to 0 as x equals to infinity. Okay? And the main contribution to that integral, so if x is large, the integral will be small. What will be the main contribution? The main contribution will come from places where this cosine, this up and downs are not as fast. Right? If these ups and downs are slightly more, are not, you see what I'm saying, right? When this is going to be larger, and whether this happens,
When x is more.
x is large.
Ah.
So the main contribution will come from the places where phi prime of t is 0. You see? So again, despite this integral have a completely different logic than the Laplace integral, right? Still the main contribution is coming from the vicinity of these points. Not because it is a maximum or minimum. Now you don't care if it's a maximum or minimum. Right? You only care about the phase to change slowly. Right? The places where the phase is changing slowly are the places where you have the main contribution to the integral. And this is how, if you, for example, if you are using Feynman path integral, this is how the classical physics emerges from the quantum mechanics. Because what it tells you is that the quantum physics, the chance is e to the I over h bar times the action, right? Now 1 over h bar is a small number. So what you want is the derivative of the action to be 0, and this gives you the Euler-Lagrange equation. Right? That's the variation over the action is what gives you the Euler-Lagrange equation. So this essentially is an integral that appears always in quantum physics, in the theory of waves, and has to do with exactly that, with and to deal with this in an ordered manner, there is here a chapter on the stationary phase method, which is equivalent to the Laplace method. I mean, very similar in spirit and also technically very similar, but for such integrals. One important difference is that in the Laplace, we were looking always for the maximum of phi. Here, both maximum and minimum, right? So, as you know, quantum mechanics implies that not only trajectory, not only trajectories of maximum action, but also trajectories of minimum action will give you, or not only those of minimum, also those of maximum. You want only extremum, right? Usually it's a minimum, but in principle, you may have a trajectory for extremum action, and they give it. Okay. So, thanks a lot. It was, for some reason, I don't know. Last year, I suffered from teaching this course, and earlier this year, I went to Yossi and told him I want to switch to another course. Maybe I will do that, but in any case, this year I enjoyed it very much. Also the course in numerical analysis, the same thing. Last year I didn't enjoy teaching, and this year I did enjoy. I don't know who is responsible for that, but if it's you, then thank you very much, and good luck in the examination.
Thank you.
So today, our last session before the exam, we're gonna cover two topics. The first one is stationary phase, and the second one is the steepest descent. So basically, stationary phase. Is the Laplacian method for the integrals that have f of t, I, x, psi of t, dt. So in this case, psi of t is the function of real argument t, and the exponent is purely imaginary. Okay. So, of course, we're gonna see the approximation as x goes to infinity. So if x is some large parameter, then this exponent is highly oscillating thing, right? And if we try to draw it, it's like this. Okay. The most of the integral is just 0 because we have approximately the same amount of positive values and negative values, and the only contribution is by the endpoints. So at the endpoints you may have some non-canceling things. And the idea is to expand psi in Taylor series, okay, around some point t naught. So if there is a point there, the first derivative is 0, we call it stationary phase point, and then you have only this term and this term. We change the variables, and eventually you have the same as Gaussian integral, but with I. Yeah, but we know the formulas. There is the name of such integral is Fresnel integral, and the value, if we integrate from minus infinity to infinity, e to the plus minus I a times s square ds. So it's a well-known integral. It's square root of pi over a times e to the plus minus I pi over 4. Okay. Yeah, that's basically the idea. If there is no point where the first derivative of psi 0, then we can just integrate by parts, and we'll take only the first part. The second part will be the next order approximation. Yeah, that's pretty much it. And the formula for if we have a stationary point, this integral is, okay, let me write actually not from 0 to infinity, but from a to b. Okay. So the formula is that this integral approximately square root of pi over x psi double prime at t naught absolute value times function f at t naught. Okay, let me use at t naught times e to the I x psi of t naught plus let me call it sigma times p over 4. Okay, what is sigma? Sigma is the sign of the second derivative. So if it's second derivative is positive at t naught, then we'll have this integral with plus, and therefore I can plus b of wave minus, so change is sigma to minus 1, and that's it. Okay, that's it for the theory, and then let's do a couple examples.
So it kind of changes if it's sine or cosine. The real or imaginary part. Because the distance would be pi over 2.
What do you mean?
Okay, so we have the complex exponent, and it could be like we have two different functions that are 2 over pi distance apart, right? With the sign, with the sigma.
No, sigma is only plus or minus 1.
Right.
Depends
So
on.
if we have plus and
Yeah.
if we have minus, the difference between the two functions is it's pi over 2,
Okay.
right? So it would be the difference. It's
Yes. Sometimes I mean that's for the case then you have only one stationary point, but if you have two of them, you need to add this
okay,
term
okay.
with the same thing, but not t naught, but t1. We will do it. Don't worry. So the first example is we have to evaluate this integral from minus infinity to infinity e to the I x t squared dt. Again, x goes to. So in this case, psi of t is t squared, right? And oh yeah, I forgot to mention that if t naught is one of the endpoints of the integral, so it's a or b, then you have to multiply this by a factor of 1/2. Okay. So it's 2t, and t naught is 0. Then the second derivative is 2 is greater than 0, then we can use the formula, right? So t is inside the domain, right, from minus infinity to infinity, and it's square root of pi divided by 2x times e to the I, and then we have to calculate the value of the function at t equals 0. So that's why we have only this is 0, and this pi over 4. Okay. Yeah, there is a mistake or two. So that's why the final answer is square root of pi over x e to the I pi over 4. Yeah, and that's basically it. Because this is the Taylor expansion of psi. See, there's only like 3 terms, right, in Taylor expansion. We can't calculate psi. I mean, we can calculate third derivative of psi, but it's 0. And the question is how we can. This is the leading order. How we can add more terms. So how we can find what are the subdominant terms, and we will do it. So remember this answer for this integral. We will use steepest descent, or steepest descent method, and we calculate subdominant term. Okay, and let me just write that this term is order of 1 over x. Okay. Okay, let's do the next one. Example number 2. Integral from 0 to 1 of cosine of x times t squared dt. So the trick is to instead of cosine exponent and take the real part. Yeah. So it's the same as real part of this integral with complex exponent, right? So basically we know already the answer for this integral, right? But we have to be careful because at this point stationary phase at the endpoint. So that's why we have to multiply by a factor of 1/2 and then take the real part. And the real part of this exponent is just cosine of pi over 4, right? And cosine pi over 4 is 1 over square root of 2. Right? So it's 1 over square root of 2 and then 1/2 and then is pi over x. Okay, so it's 1/2 square root of pi divided by 2x, and that's the answer for this example. Then we have to calculate approximation for Bessel function. So Bessel function of order 0 at x goes to infinity. It's 1 over pi, integral from 0 to pi,
to the
cosine of x cosine theta. So again, we want to see here not cosine or sine, but complex exponent. That's why I write it as 1 over pi real part of integral from 0 to pi e to the I x cosine of theta d theta. Okay, now let's find the stationary points. Psi of theta is cosine of theta, then psi prime of theta is minus sine of theta, right? Equals 0. So then theta equals
0 pi.
0 pi. So in this case we have two stationary points and both of them endpoints. Okay? So that's why we'll write like this. Okay, the second derivative, psi double prime of theta is minus cosine theta, and then it's minus 1 and plus 1. Okay, and theta is 0 is minus 1, then theta is pi is plus 1. Okay, then 1 over pi. Both integrals will have factor of 1/2 because of endpoint, so that's why it's like 1 over 2 pi, then real part, and then square root of 2 pi divided by x times the absolute value of this. So in both cases it's just 1, and then I have to multiply it by e to the I x times function at the first stationary point, so which is cosine of 0 is 1, so just x. Then the sign of the second derivative for pi is -1 and minus pi divided by 4. Okay, that's the first one. Then plus contribution from the second stationary point. Then theta equals pi. That's 2 pi over x e to the I, and then at point theta equals pi. The function itself equals -1. So that's minus x, and the second derivative with plus. So then plus pi over 4. Okay. And now I see that I have some of the exponents over 2. I can convert this into cosine, and then the real part of the cosine is cosine. Right? So the answer is 1 over pi times the square root, or we can put this pi inside, right, and then it will be 2 divided by pi x times cosine of x minus pi over 4. Okay. Yeah, and a last example here for area function. So we're going to see asymptotics of area function for large x. I guess it's 5. 4. So f area function minus x is 1 over 2 pi integral from minus infinity to infinity. E to the I t cubed over 3 minus xt dt. Again, x is large and goes to infinity. So sine of t cubed 3 minus x times t, and we're looking for stationary phase, t squared minus x equals 0, and t is plus minus square root of x. And this is moving maximum. We have to rescale the change of variable, right? So we define s as t divided by square root of x. Okay.
But if we said earlier that the general integral was e of I x psi.
Yeah.
So shouldn't be like, should you take one?
Yeah. That's why. I'm gonna do it right now. So if we now rescale the integral or change a variable if you want,
okay.
we will get the pretty much integral in this form.
Yeah.
Just a minute. So then square root of x ds equals dt. And now let's plug in this into integral. So it's gonna be square root of x over 2 pi, integral from minus infinity to infinity, then e to the I, and then, so t is square root of x times s. Okay. So t cubed is x to the 3 halves times s cubed divided by 3, and minus x times square root of x times s 3s. And now you see that there is x to the 3 halves here and x to the 3 halves here. I can write it in this way. Infinity e to the I x to the 3 halves s cubed over 3 minus s. Okay. Yeah, and generally speaking, in this method of stationary phase, it doesn't matter if you have x or x to the 3 halves, it just has to be the large parameter, and that's it. Okay. So now psi of s is s cubed over 3 minus s, and then our stationary points are plus and minus 1. Again, we have 2 stationary points, both of them inside the integration domain. Okay, then we'll have 2 contributions. And yeah, psi double prime is 2s, so it's plus or minus 2. Okay, then square root of x over 2 pi from the first point, then s equals plus 1. We have square root of 2 pi divided by x times 2, and e to the I x times function at stationary point. So then s equals 1. We have 1/3 minus 1, so minus 2/3. Minus 2/3. And then second derivative of the plus sign, then plus pi over 4. Okay, that's the first contribution. The second contribution will have the same prefactor, and then plus e to the I, then at the point s equals minus 1, we have minus 3 halves plus 1, so it's plus 2/3. Yeah, plus 2/3, so it's x times 2/3, and the second derivative is negative, so minus pi over 4. Okay. And again, see the sum of the exponents, so I can use the formula and write it as, by the way, you have to be careful with this x. Okay, in this case, because we have x to the power 3 halves, here we also have it 3 halves. Okay, if you have some large parameter lambda instead of x in this formula, you'll have lambda. Okay, so it's x. Let's combine it actually. So pi, I think it would be like 1 over, and here is pi x to the, so 3 halves, so it's like 1/2, I think, times cosine of 2 thirds x minus pi over 4. Okay.
That x also should be in the power of 12.
Let me think.
And you can
Yeah.
do it both ways, right?
What do you mean?
It could be like that, or it could be to the power. Because it's the exponent, so it's just.
No,
right? What do you mean?
So when we use the expansion, right, we expand in this method, we have e to the some large parameter, then I and psi of t, right? And this large parameter is in the every term of the expansion multiplied. We multiply it by every term, so that's why when I write this, I also have to multiply. So it's the same, yeah. 3 halves, that's 3 halves. Yeah. Thanks. Yeah. Okay. Now let's talk about the steepest descent. So now we want to approximate integral in this form. And d f of t e to the x times rho of t dt. Okay. And the thing is that rho now is complex function. So it has both real part and imaginary part. I call real part of the function by phi of t and imaginary by psi of t. Okay. So sort of a very general case, and it combines both ideas of Laplace integral and stationary phase method. Okay, but do you know the idea of steepest descent?
You have to do the derivative, right? Just include it. So
Yeah, but I mean more intuitively. What we're gonna do, and why it's the steepest descent.
you want the contributions from the minimum. Right?
Yeah. So what I have initially? Initially I have integral. So let's now treat t as complex variable. So it has two components, okay? And my complex plane is uv. Okay. So initially I have real integral, right? So I calculate like from a to b. Okay. That was my path, right? And the idea of the method is the following: that now I want to find a new contour, like this one, for example, and along that contour, psi of t is constant. Whereas psi of t is my face, my imaginary face, my oscillations. Okay. So if we can find this such contour, when what happened with the integral from a to b, or maybe it's better to now write it as well, contour integral, and f of t e to the x phi of t times e to the I x psi of t. Now along this contour, psi is constant, right? So I can simply move it out from the integral, right? And what I left with, just Laplace and integral, right? And I know how to calculate it, that x goes to infinity. That's the thing. And we usually, rho is so-called analytic function. So in the as complex function, not like that it has Taylor series. In the complex way, means that there is a Cauchy-Riemann equations and all of these things from complex analysis. So, and the beauty of it is that for this, along this new path, then phase is constant, stationary. This function phi has sort of a steepest descent. So it goes from its maximum value to its minimum. Okay. Yeah, that's basically the idea of method. And when we talked about stationary phase method, we just wanted to psi be 0 at some point, right? But here we wanted to psi to be constant along the whole way, whole path. So in a sense, this steepest descent is we can call it also super stationary phase. So the phase doesn't change at all, while in the previous one we just fix the rate of change it. Okay. Now let's solve actually. Let's find the subdominant terms for this integral. Okay. So leading order we can find from the stationary phase method, but now let's do steepest descent. Okay, and steepest descent will give us leading order and the next order correction. Okay, now t is complex variable, right? So t is u plus iv, right? And let's have a look at this function, rho of t. So rho of t is t squared, or u squared minus v squared plus 2i uv. Okay. So now we have let's plug in this into integral from 0 to 1 e to the ix times u squared v squared plus 2i uv dt. Okay, and now I have integral from 0 to 1 e to the minus 2x uv times e to the ix u squared minus v squared. Okay, So now I have my function, my real function and my complex function, and I want to find the contour that give me psi constant, right? Let's actually draw complex plane, okay? And initially my integral was from 0 to 1. Okay, and I want to find some path along which this will be constant. But there is a problem, and the problem is that at this point and at this point the value of psi is different. You see? At the point 0, 0, psi is 0. But at the point 1, 0, psi is 1. So that's why we cannot find only one path that connects these 2 points, because along this path, psi will change. We don't want it, okay? But there is a trick. We can actually use several paths and combine them into one, okay? But we have to add some path that along which psi changes, but the contribution of it is negligible. Yeah. Okay. So let's do this trick. Firstly, we have add 2 paths along which psi is 0 and psi is 1. Okay. So what are these paths? Let's have a look. So then psi is 0, you have u square minus v square equals 0, and then v equals plus minus u. Okay. So let's draw them. That's like 45 degrees. These 2 lines. Right? This one is v equals u, this one v equals minus u. Okay? So psi doesn't change along these 2 lines. Okay? And now let's find the equation for the next one. So psi equals 1 equals u square minus v square. So v square equals plus minus square root of u square minus 1. Okay. So it's hyperbola. Looks like this. Okay. The upper branch is v equals plus square root of u square minus 1, and this branch is minus square root of u square minus 1. Okay. Now the trick is that we add to these 2 paths of constant psi, we add this kind of a bridge between them, okay? And this will be the whole path, okay? And what is the height of the bridge? The height of the bridge, we can call it v, okay? At this point, I mean, along this line, psi is changing, right? But we will see that as v v goes to infinity, the contribution from this part of the path will be negligible.
There are
So it
no
goes-
other poles, right? That's what you mean.
Hmm?
There are no poles, so you can take it to infinity.
Yeah, I mean the function itself is analytic, so see, there's no problem with that. Yeah. Okay, so yeah, and we'll see why I mean you can connect it like this, right? You can draw also here bridge. It's the same, but we'll see that this is the only right choice. Okay? Because we want to this function phi actually descend, not grow. So yeah, let's see. Okay. Now let's calculate. Basically, let's calculate three integrals along C1, C2, and C3. Okay. So the first integral along C1. Okay, inside it we have e to the minus 2x uv, e to the ix u square minus v square dt. Okay, so what happened along with this line? Okay, v equals u, and this 0, and this exponent is just 1. Okay, and then we have to multiply u times v. Okay, we have to change, so dt is du plus ev, but along again C1, u and v are the same thing, right? So that's why I can write it like 1 plus I times d. So half integral from and v, we change it from 0 to infinity. Okay, so from 0 to infinity, then I have this factor of 1 plus I. Okay, 1 plus I, e to the minus 2x v squared dv. Okay, and this is just
The Gaussian.
Gaussian, yeah, indeed. And x goes to infinity, right? And I mean the maximum contribution at the vicinity of point of view. Yeah. So we can write down the answer. So it's 1 plus I times square root of pi divided by 2x. Yeah. That's I think I forgot 1/2 because it's not from minus infinity to infinity, but yeah. Okay. But I can rewrite this 1 plus I and 1 over square root as
Exponent.
yeah, exactly. So it's just e to the I y over 4. This is the leading order that we have from the stationary phase method. Okay, it's exactly the same. So from C3 we'll get the next order approximation,
Right.
and C2
Will be 0.
will approach 0 as v approach infinity. Okay. So now let's show it actually that the integral over S2 is negligible. So E2 is integral C2 and e to the minus 2 uv times x e to the ix u square minus v square dt. Okay, so along this way, this path, what do I have? I have v some constant, right? But u is changing from some, let's call it this point u1, this point u2. Okay. So then, okay, v is constant, but u is changing from u1 up to u2. Okay. So therefore dt is du plus ev, so du, because this is just a constant. Okay. So maybe it's better to find the absolute value. Okay, so let's estimate, not calculate exactly, but estimate. So what is the estimation? First of all, the absolute value of this integral is equal or smaller than this integral. And because this is just 1. Okay. Yeah. Now, so we can move to this, right? From u1, u2, u, right? And it's just a simple integral, right? We can calculate it. But the thing is that x goes to infinity, v goes to infinity, and we have like exponential small thing. Okay. So that's why this guy goes to 0 as v goes to infinity. And that's exactly the thing why I choose the upper bridge, not the lower bridge. Because for lower bridge, v would go to minus infinity, and this integral will blow up. Okay? Cannot neglect it. So that's the thing. Okay. And now let's calculate the last part, C3. So my phrase integral C3 e to the minus 2u vx e to the ix u square minus v square dt. Okay. So now I think we know that I think it's better to solve u with respect to v. So v vice versa. U is square root of 1 minus plus, right? 1 plus v squared. Yeah. And now let's use it. So dt is d of u plus iv, and u in terms of v along this path is square root of 1 plus v squared plus e. Okay, and it's v over square root of 1 plus v squared plus I dv. Good. Now let's plug in all those things into the integral. So E3 is so V changes. So we're going from bridge to point 1. So V goes from infinity to 0. Okay? So lower limit of the integral is now infinity, and upper is 0. Okay? Then we have e to the minus 2 x v times square root of 1 plus v squared, right? And then instead of dt, it will be v over 1 plus v squared plus I dv. Okay. That's exact solution. Okay, so to find better approximation, we can expand all of the terms, right? And again, the maximum contribution is at the vicinity of this point, right? Then the most brutal approximation will be to just forget about this v squared, forget about this term, right? Just the very leading order, okay? We can write with minus from 0 to infinity e to the minus 2 x v times I dv. Okay. I just throw away this term, this I approximate as 1, and that's my integral, okay?
How did you do that approximation?
So the main contribution here is around 0. So
Okay.
that's why I just said that, okay, we're interested only at small v's. And
Okay.
that's why this is small compared to 1. I can throw it away. This is small compared to 1. So
Okay.
that's it. Okay, so now we have just simple integral, right? And it's like
I over 2x, right?
You have extra minus.
so it's like I over 2x, I guess.
With a plus, right? Because you have to take down one. Yeah.
There are 3 minuses. So
Yeah,
the
yeah.
first one here,
Gotcha.
the second here, the third, the limit. Yeah, and that's the next order correction. So the linear order is x to the minus 1/2. The next order is x to the minus 1. Okay, and because x goes to infinity, this is subdominant with respect to this one. And if you want to find the next corrections, you can just be more careful with the approximation of these guys, and yeah, that's it. That's the idea of the steeper descent. So even though you cannot find the one contour along which you have constant psi, you can make a trick where add some bridge between those two and show that along this one the contribution of it actually goes to 0. Okay. Yeah, I think that's it. thank you. That was the last tutorial of this course. Yeah, good luck on the exam.
Thank you.
Thanks.
There will be 3 questions, right?
The questions, and I guess
No question.
3 hours.
Without any material, it's like
Yeah, it's closed book. Yeah. But again, for example, all of this stuff with the integrals, it's pretty much the same logic, that you have some function into exponent, and you have some big parameter, and then you expand the function before the big parameter, and then so that's the basic idea and all the formulas. So you just have to know the Gaussian integrals basically, and some Fresnel's integrals. For the boundary layer, there is also like very intuitive algorithm how you can find the uniform approximation. What else? I think you all of you will succeed. So don't be scary about the exam. By the way, have you seen that I uploaded on Lemida the past exams?
Yeah.
No?
Can you send it?
Yeah.
Thanks.
Just send me,
Yeah,
write me a message, okay?
Yeah.
Yeah. So just you can solve the previous years, past years, and that's basically the level of the exam this year too. Yeah. What time do you have exam? What day?
It's a
It's
Sunday.
Sunday.
15th of February.
15th.
Yeah, that makes sense.
The Sunday.
Okay.
So
I remember it's a Sunday. I think it's at 4.
It's the 15th.
Yeah, the 15th. I'm seeing
Okay. So you have time. More a little bit more than a month, half a month. Yeah.
It's at 4.
Okay.
today,
So no questions. Thank you.
this session we looked at the lecture of the imaginary.
Steepest descent?
Yeah.
Yeah, I know. But just Nadav don't like this topic.
Oh, it's
so-
okay.
But someone have to teach it. You know? So if Nadav cannot, so I have to.
Okay.
Yeah, I think you uploaded twice the tutorial
The same?
11.
11?
Yeah, like the last one.
Maybe. I have to check. And I think I will not upload homework 12.
Oh,
No. Please.
Yeah.
Yeah, a lot of exams.
Yeah. You have.
Enough exams. to
Yeah.
do.
Yeah. Okay. So then.
thank you.
Thank you.
Thank you. Thank you a lot. Just like I can ask the questions.
Yeah.
I think it's strange. Start going for the exam. We have something like that. 8 equals 0 first.
Okay.
So when I solve it, we do something like that and we can solve. But, why I can't solve it